Hello my dear students, I welcome you to NEET World. So today we will be discussing about mesomeric effect. In the last class we have discussed inductive effect and its applications, and the next we have discussed about resonance, right? Okay, so this is one of the most important topic for organic chemical reactions in order to understand how the chemical reactions are taking place. So this topic will be very useful there. Okay, so I will show you once after completing this discussion. So I will show you some chemical reactions also. So without knowing the name of exact the name of that particular reaction, we can able to tackle with using this concept itself. Okay, so let us follow this class properly and let us make it more clear. Okay, so what exactly mesomeric effect here? So in the organic compounds we know conjugated systems are there. So what do we mean by conjugated systems? See, for example, so we will be seeing some compounds having alternate double bond with single bond, again double bond. So this is what the alternate double bonds, right? So this kind of systems or compounds are considered to be conjugated systems. Okay, so what is the difference between conjugated and isolated? See, so same thing I am writing in this manner. See, so this can be considered as isolated system. See here, the double bond and this double bond are alternately positioned, and in between we have a single bond. But here this double bond, this one and this one and this one are positioned at isolated position. It means here delocalization of pi electrons is not possible, but here we can delocalize this pi electron like this, right? So this kind of systems are called conjugated system. What is it? Conjugated systems, and these are called as isolated systems. Okay, so conjugation or the delocalization of pi electron is possible only in conjugated system. Okay, so you can remember conjugated dienes are more stable than the isolated dienes because of its conjugation of these pi electrons. Now in this conjugated system we need to discuss about mesomeric effect. It means mesomeric effect is possible in conjugated systems only. Okay, so now what exactly mesomeric effect? So in this conjugated system, just I want to represent in this manner. So in this conjugated system, the delocalization of these pi electrons takes place. Therefore the electron cloud, the movement of electrons takes place and creates electronic distribution like this. Okay, the movement of charge electrons are taking place now like this. Okay, so this phenomenon is known as mesomeric effect. Okay, so now to this compound, for example to this particular conjugated system, if a group G is attached, so what I am saying, to this conjugated system, I am attaching a group. Let us say a G group is attached. On this G group, let us say it is having some lone pair electrons on it, something like this. Okay, now this lone pair or non-bonding electrons can be given into this system now. So this group G is donating its electrons into the system. Now see, when it is donating electrons into this pi electrons, I mean this conjugated system, what happens? The system is getting negative charge on it. So it means electron density of this conjugated system is increasing. Therefore I should call this group G as electron donating group or electron releasing group. Okay, why? Because it is releasing, this group G is releasing electrons into the system. Therefore system, it means system means this organic conjugated compound or like this compound. Okay, it is getting a negative charge on the compound. See here, if I write like this, see, when it is attached over here G, it is donated, therefore it is becoming a double bond. So when these electrons, lone pair electrons are coming here, this pi bond should be shifted over here and we have something like this. Okay, see, into the conjugated system we have a negative charge on it, right? Okay, and this should gain one positive charge. Okay, now this negative charge again can shift from here to here. Okay, here we know it represents CH2 group. So therefore we will be getting one more conjugated resonating form like this. So I just want to indicate G. So see, between G and carbon we have a pi bond like this, and this is coming over here. So write double bond here. So now this pi bond is shifting to here as a negative charge. So this is how the resonating structures are formed, right? So what this group is here, it is donating its non-bonding electrons into the system or releasing into the system. Therefore I can call this group as electron releasing group. Okay, if the conjugated system is attached with one electron releasing group, and this effect is called as plus M effect, positive mesomeric effect. Okay, in some cases these groups, they will drag the electrons towards itself, it means they withdraw the electrons towards itself. In that case we should call that group as electron withdrawing group. Let us consider, so I am writing here, so this is a conjugative system, so attached to a group G dash. Now let us say this group G dash is withdrawing these pi electrons from the system. So it means I can call this group G dash as electron withdrawing group. So when it is dragging these electrons towards itself, so it is creating a positive charge on this carbon, because this pi electron shifting from here to here. Na? So here we will be getting a positive charge. So like this you have to write. See, from here to here this bond is shifted, pi bond is shifted, so therefore this G dash is getting a negative charge, and here the carbon is getting positive charge. So in the system, in the previous case we have negative charge, but here we have a positive charge. So what I can say, it is withdrawing the electrons, the group G dash is withdrawing the electrons towards itself and creating electron deficiency in the conjugated system. Now this cation is in conjugative position with this pi electrons. Okay, now cation pi electron conjugation takes place to give this species. See, now this bond can move over here and will be having, see, already we have a negative charge on this G dash, so I am writing like this, and this will be shifting over here, and now this CH2 group will be getting a positive charge. So like this carbocation delocalization takes place. Okay, so when electron withdrawing group is present, so we will be getting a positive electron deficiency in the this conjugative system. But when we have electron releasing group, that will release the electrons, and therefore the system is getting more electron density and with negative charge is represented here. Okay, so means we have two types of effects, two types of mesomeric effect. One is plus M effect and another one is minus M effect. So in the first case it is plus M effect. When electron releasing group is attached, so we should say that as plus M effect. Okay, so when electron withdrawing group, this G dash is electron withdrawing group is present, so we should say this is minus M effect. So I hope these two effects are clear with this normal conjugative systems. Let us look deeper into this, exactly what electron releasing group examples and electron withdrawing group examples. Okay, so here I have brought electron releasing groups or plus M effect showing groups and electron withdrawing group or minus M effect showing groups. Okay. So here let us say I am just considering benzene ring here. So we know benzene ring is also a pi conjugative system like this. Okay, to this group I am adding a G group. Let us say our G, instead of taking G, let us take one of the group from this, one of the example of electron releasing group. So this G can be any of these groups. So now one thing is common, all of this is they are having some lone pair non-bonding electrons on them. See, here on oxygen we have lone pair electrons, here also, everywhere we have some non-bonding electrons on this group. Therefore, these non-bonding electrons or the lone pairs can participate in the conjugation with this pi electrons of benzene ring and increases the electron density of this benzene ring. I hope this is clear. So let us say here I am taking phenol. It means on benzene ring, phenyl ring we should have one, on phenyl ring we should have one OH group like this, right? Okay. So now these lone pair electrons of this OH can be donated into the ring, right? So when it is donated into the ring or delocalized into the ring, and this pi electron cloud will be shifting over here and we are getting a negative charge on the ortho position. So I hope you know what exactly ortho position and para positions. Okay, I will tell you, wait. Okay, see, on the phenyl ring, if any group is attached, the adjacent position is called ortho and the third position is called meta and the fourth position is called para position. So the negative charge here it is at ortho position. Okay, now this can be again donated here, and the pi electron, see, so you should be aware how we are writing this pi electron shift here. While writing the resonating structure, you should be more clear. See, I am writing here, therefore we will be getting a structure, a resonating structure like this, like this. See, when it is shifting here, you should represent over here, and the pi electron cloud is moving here, so write the negative charge here, and this write as such. Okay, now again one more resonating structure is also possible. So just take this negative charge over here, so we are getting a pi bond over here. It means this should move here, and we will be getting a resonating structure like this. See, here we have one pi bond, and here OH, oxygen with positive charge, and here we are getting new bond, pi bond, and this will be having a negative charge. I hope this is also clear how we are writing. And the next thing is, so you can write it like this, and oxygen will take back its pi electron, therefore we will be getting something like this, OH. So this is how the resonance stabilization takes place. Mesomeric plus M effect will be taking place in the conjugative systems. Okay, okay, I hope this is clear. Now the resonating structures, between two resonating structures you have to use this kind of symbol in order to indicate the resonance. Okay, so two sides arrow mark should be there. Okay, so double headed arrow you have to use. I hope this is clear. So here how many resonating structures are there? 1, 2, 3, 4 and 5 resonating structures are possible. So this is how you need to write the resonating structures of any particular compound. Okay, so now here when electron releasing group is there, on the benzene ring, on the phenyl group will be having negative charge. It means we can say electron releasing groups increases the electron density of the system or the conjugated system or the benzene ring here in this case. So I can write electron releasing group. So what it will do? It will increases electron releasing groups, increases electron density in the conjugative system. Here when we are talking about benzene ring, so you can write, so electron releasing groups increases electron density. See here I told you this will be second position. If this is a group, it is at adjacent position, that is what the second position, you can say ortho position I told you. So increases electron density, negative charge is at ortho position and also at para position but not at meta. So it means electron releasing groups increases electron density at ortho and para positions. It means there is no mesomeric effect at meta position. You should remember that we haven't seen any effect at the meta position. See, in any of this structure there is no positive or negative charge at this third position or the meta position I can say. Okay, so it means mesomeric effect can be seen only at ortho and para positions, not at meta position. Okay, this is clear. I hope this is clear. Now let us discuss about minus M effect or electron withdrawing group on this conjugative system. So here also let us say we have again benzene ring. So to this I am adding a group here, group G. So this group G, let us generalize. See, the common thing about all electron withdrawing groups is, see, the common thing is listed here is the atom G is connected with conjugative system with a pi bond with another group G dash. Okay, now this G dash will be having more electronegativity than this G. Therefore, this G dash will withdraw the electrons towards itself and creating a positive charge on this. Okay, so here if we want to talk in detail, so let us see this example. So let us insert here nitro group. So nitro group I am adding here nitrogen, and here we need to write double bond oxygen, and here I am writing one more with dative bond. See, we know nitrogen, what I told you, this G group, let us say nitrogen is attached here and which is attached with a pi bond to the other more electronegative oxygen atom, right? It means the pi electron here will be taken towards oxygen side and creating a positive charge on the nitrogen. So we know nitrogen is more electron than this carbon, therefore this nitrogen will drag these pi electrons towards itself. It means from the ring this nitro group is dragging the electrons towards itself and creating electron deficiency in the benzene ring or phenyl ring, right? So it means the conjugative system should be written like this. See, O minus, this will be, so write this as such. Now see, here we have like this. See, this bond should shift here, therefore a positive charge is seen at this ortho position. I hope this is clear. Okay, then next write the other resonating structure possible. See, this positive charge can be stabilized by this pi electron, right? So write that this, whatever the things are there, I have written like that. So when this is shifting over here, so what happens? So here we will be having a pi bond, and this bond is this carbon is getting positive charge because it is disconnected with this pi electron. Therefore I am writing a positive charge over here, and here we have a pi bond like this. I hope this is also clear. Okay, then next, what is the next conjugative resonating structure here? So now I can shift from here to here, and this carbon will be getting a positive charge. Okay, here write the things as it is first. Okay, the remaining thing here is, so this should be shifted over here. It means here we are getting double bond and here a positive charge. Okay, so finally, so you just shift this back and this will be written like this. Like this. So how many resonating structures here also? 1, 2, 3, 4 and 5. So these are the 5 resonating structures we can write when electron withdrawing group is present. Okay. Now one thing you need to remember is, so when electron releasing group is there is negative charge in the system, but when electron withdrawing is there, so they are dragging the electrons towards themselves. See, electron movement is towards the electron withdrawing group. Here it is into the ring side, but it is away from the ring. It means it is electron withdrawing group is decreasing the electron density or creating a electron deficiency at ortho and the para positions. Ortho and these para positions. It means we can write electron, so what we can write? Electron withdrawing groups are decreasing the electron density, of the conjugative system and creating a positive charge, that is what electron deficiency, right? Okay, so now I can write when it comes to benzene ring, this phenyl ring, so what we can write? Electron withdrawing groups decreases electron density, especially at what positions on the benzene ring if we talk? So at ortho and para position only, there is no effect at meta position. So I can write electron withdrawing groups decreases electron density at ortho and para positions. I hope these two statements are very clear, and this should be this should be very helpful for our upcoming examples. Okay, so just go through this once again and take a screenshot if you require. Okay, so let us discuss few more things about the mesomeric effect. Okay, so now I have told you there is positive mesomeric effect, that is plus M effect and minus M effect. So when it comes to plus M effect, so now here I told you this many groups are there, so this many electron releasing groups are there. So along with this we have some other electron releasing groups also. That's why what I generalized here. So if if for example this is a conjugative system, so what I told you, if this is a conjugative system, so any group G is attached, on this group G any non-bonding electrons, maybe it may be anionic form or maybe having some lone pair, so it can be G minus, it means these minus electrons, these negatively charged electrons also can be donated, or with neutral form it can be having some non-bonding electrons, right? So this can also be participating in the resonating structures, right, or stabilization factor. Okay, so now, so these are the different groups which can be attached to that conjugative system. Let us say on benzene ring, let us put this G dash, like G. So G can be any of these compound, any of these groups. Okay, so now which will be showing more mesomeric effect, I am asking. So it was found to be O minus will be having more mesomeric effect plus M effect than this NH2, then next NHR or NR2 and OH, OR, something like this, amide group or ester group, whatever it is present on this benzene ring. This will be the order you need to follow. It means, I just want to give you one clarity. O minus is there, and let us say one more group is there. So here I am writing OR, and I am writing one more thing, COR. So some random groups I have taken. So A, B, C. Okay. Now tell me, more effective conjugation or more effective mesomeric, positive mesomeric effect or plus M effect takes place in which of these? So write the order. So it means, I told you, when there is negative charge, the conjugation is very flexible or very easy. It can be donated easily towards the ring. Therefore, mesomeric effect, the plus M effect will be more in A when we compare with B and C. So that is how this order will help us. Okay. Now I told you OR is here, it means alkoxide group, and here we have ester group here. Okay. Out of these two, I am saying this OR will be participating in the resonance more effectively than this. Why? Because see, these electrons over here will be in resonance with, is in conjugation with this ring electrons, ring pi electrons, and also there is one more possibility. So this can be, see, one pi bond is there and alternate single bond and this lone pair. So this side also conjugation may takes place. It means for this particular atom, the conjugations are at both sides. It means the electron density which is coming this downside towards the ring is relatively less, because it can be participate this side and also the other side. But here these electrons are completely involving in the conjugation with ring electrons only. Therefore, I can say mesomeric effect plus M effect can be more in A, because this negative charge is purely involving here, A, then B, then C. I hope this is clear. Okay. Okay, I hope this is very clear. If you have any doubts, you can write in the comment box. Okay. Then next, so you have to remember this order. So just take a screenshot, it will be helpful again. Okay. So now we will be talking about minus M effect. So similar to whatever we discussed. So after completing of this discussion, I will be showing you some question. There it will be very helpful. Okay. So let us see. So to this benzene ring, here I have one nitro group, NO2 group. See, nitro group is having minus M effect like at maximum when we compare with the other groups. Now other one I have, here I have aldehyde group, COH. This is aldehyde, benzaldehyde, nitrobenzene. Okay. So now out of these two, the mesomeric effect will be seen in which case, more mesomeric effect to mesomeric effect is more in which case. So it will be more in first case, because this is having minus M effect, both are minus I groups, minus M groups only, right. See, there is no lone pair electrons on this nitro group, I mean nitrogen of nitro group and carbon of like aldehyde group. Therefore, this only will withdraw the electron. So I can say this is electron withdrawing group, here also works same. So now, but the effective, this is having, nitro group is having more strength to withdraw the electrons. Therefore, I can say the more minus M effect is taking place in A when we compare with B. So I am writing like this. Okay. So this is also clear. So based on this concept only, we will be having some questions we will do after some time. Just hold for some time. Okay. Now, so when a plus M group and a minus M groups are at meta position to each other, then they are not in conjugation with each other, but conjugation with the benzene ring. Yes. So what I told you, the whatever the mesomeric effect is there, that will not be observed at meta position, I told you. So it means, let us say here I have a group like this. So let us say here we have O minus. Okay. Now here we have some aldehyde group, let us consider. So this is plus M group And what about this group? This is minus M group. Now tell me, so I told you that when these electrons are in conjugation or involving in the resonance, so I told you the negative charge can be seen at ortho position with respect to this group and para position with respect to this group. Here also this can be also considered as ortho position only, but there is no effect at this position and at this position, right? So these are what? Meta positions. No electron withdrawing group, I mean electron releasing group, oxygen like O minus is conjugation with these pi electrons, but it is not in conjugation, this O minus is not in conjugation with this aldehyde group which is at the third position, because at the third position, that is at the meta position, there is no mesomeric effect. I hope this is clear. That is what I am stating here. Okay. Similarly, when this carbon like aldehyde group, see, oxygen will withdraw these pi electrons and create a positive charge on this carbon, right? Now see here, this bond can be shifted here. Okay, so when it is shifting there, so where are the positions, what are the positions we can see the positive charge at? So we can see the positive charge at these positions. Just give a minute. So when it is withdrawing the electrons, we can see the positive charge. See, when it is withdrawing this side, so we can see positive charge over this position which is ortho, and next position can be when it is giving here, we will be seeing positive charge over here, but not in this position and not in this position, again over here. So it means these two positions are what? Ortho to this, and this fourth position is called para to this. So O minus and aldehyde group is not in conjugation. That is what the statement is explaining. Okay, next. So what are the applications? So this is a simple discussion of mesomeric effect. Let us discuss more in detail about their application. So these applications are highly useful. So I will be giving you clear cut idea on these applications first. So just try to follow this. Okay. So now let us study what are the applications here. So first one is stability of intermediates. So now what are the intermediates we have? So we have discussed clearly about intermediates, about carbocations we discussed, then next carbon anions we discussed, and then next we also discussed about free radicals, right? So these are the three main intermediates we have to focus here first. Okay, so if anything is remaining we will discuss later, but we need to discuss about this clearly first. Okay, then next here one more application is there, acidic strength of organic acids. Let us say carboxylic acids are there, and phenols also show acidic nature, so we need to discuss about that also. And the next thing is basic strength of organic bases. So example can be aromatic amines or aliphatic amines, so we need to discuss about the basic nature of amines. Then next, how this bond length will be affected by this mesomeric effect we need to discuss. Okay, this one also helpful. Okay, then next, reactivity of organic compounds. I told you now at the beginning, so what I told you, so even though we don't know the exact name of that particular organic reaction, by the concept of this mesomeric effect or the complete GOC concepts, so we can tackle those questions in the exam. Okay, so I will show you some questions also based on that. So we need to discuss the 4 applications. Okay, so let us discuss about carbocation stability first. Okay, so let us, let me complete it here itself. So first thing is stability of intermediates, and the first one is stability of carbocations. Consider. Okay, so here I have a carbocation like this. Here I have like this, and another one is within the group. I just want to mention here. So here, okay. So there is a compound like this. Let us consider. So now within the given compound, we have a positive charge over here and here. Okay, so which carbocation is more stable? So let us consider this is a example. So in this example, here I mentioned positive charge and also here I mentioned positive charge. Now tell me which carbocation. So let us consider this carbocation as X and this carbocation, otherwise just take it as. Now tell me, first of all, let us say this is A carbocation, this is B carbocation. Now decide which carbocation is more stable out of this. Okay, so now I told you, I explained mesomeric effect, just now we discussed, and also previously we have discussed about inductive effect. So using these two concepts, you need to decide the stability of these carbocations A and B. So which is more stable? So just now I told you, if there is any conjugation, then mesomeric effect will be applicable there. So here this pi electrons is in alternate position with this carbocation. Okay, so when they are alternate position, we can call it as conjugative system. So only in conjugative system we can see the mesomeric effect. So this can be stabilized like this. It means this is having plus M effect. Okay, now see here, this positive charge is at isolated position with this pi electrons, which means it cannot participate in this conjugation like this. Mesomeric effect is not seen in this case. Okay, so it can be having only alpha hydrogens here, which we need to discuss about hyperconjugation later. So now as of now we know this is what inductive effect we have discussed. So here we are seeing only plus I effect. Okay, here we have minus M plus M effect. So which effect is dominating effect? I told you this mesomeric effect is dominating effect. Therefore out of these two carbocations, carb B is more stable than this A. I hope this is clear. Okay, if not, we will see few more example, it will be giving you more clear idea. Okay, so here let me take CH2 plus. Okay, and one more thing I am taking here, CH2 plus. So now tell me, out of these two, which carbocation is more stable? So here just check here, these pi electrons and this positive charge is at alternate position, that is what we can say conjugative position. So it can be stabilized like this, and we can get a resonating structure something like this. See, when these pi electrons are shifting here, so you can write like this, and this carbon should get a positive charge on it. So this is how it is getting stabilized. But in this case we have only sigma bond, which is alkyl group, which is connected to this methylene carbocation. So it can be stabilized by these two hydrogens by hyperconjugation. I will tell you in the next class what exactly hyperconjugation. And I can say alkyl groups are plus I groups, right? So it is having only plus I effect, but it is having plus M effect. So I told you plus M effect is more dominating than plus I. Therefore this will be more stabilized carbocation than this. So I can say A is more stable than B. So same story you can apply here in this example, that will be giving you more clear idea. Okay, so let us discuss few more examples now. Okay, so here, so what is this? This is a benzene ring. So let us write like this first for understanding purpose. So here I am writing positive charge. Okay, so this carbocation you should be call it as benzyl carbocation. Benzyl carbocation. Okay, next thing is you can take this carbocation also and write positive charge over here, and let us insert one group at a para position. So let us say we are inserting here OH group. Okay, now one more thing you can take here is CH2 plus, and here just insert one nitro group. Okay, now we need to decide the stability of these three things. Okay, so which is more stable carbocation here? So I told you carbocation means it is electron deficient site now. So this electron deficient carbon should be stabilized by a group which will be releasing electrons towards it. It means we required electron releasing group to stabilize this benzyl carbocation. So it means here some groups should be present either at ortho position or at para position. Therefore they can release the electrons into the ring. That electrons will be donated to this or shifted towards that benzyl position carbon. Okay, like this. So when it is shifted here, we are getting a positive charge here. So this can be again stabilized by this one. Okay, like that. So this lone pair which is present on the nitrogen can be denoted into the ring. So I can say this is electron releasing group. So we can write electron releasing groups increases stability, already discussed during the studying about reactive intermediates. So electron releasing groups increases the stability of carbocations and also free radicals. What I am saying, electron releasing groups increases stability of carbocations and free radicals. This is electron releasing group only, no? So it will increase stability. See, here we don't have any electron releasing or withdrawing group. So here we have electron releasing group or donating group. So I can say this B is more stable. Okay, then A, and least is C, because this is positive charge and this group is what? Electron withdrawing group. So the group will withdraw the electrons towards itself and creates more electron deficiency on this positively charged carbon, which will further destabilizes the system or this compound. So I can write B is more stable, then A, least is C. So this is how you need to decide the stability of carbocation. I hope this is also very clear. Okay, so let us discuss few more things. Okay, so let us go to carbene anions. So one thing you should remember here, more the number of resonating form, more the resonating structures, RS means resonating structures you can consider, more is the stability, more is the stability. So this is how we need to make. Okay. So let us discuss few more things about carbene anion. So by end of this session, I mean after studying hyperconjugation also, we will be solving more questions related to carbocation and also other intermediates too. So but as of now, just have an idea, a clear cut idea how this exactly this mesomeric effect is playing here. Okay, or deciding the stability order. So let us say I have a carbene anion like this, CH2 minus. So we should call this as benzyl carbene anion. Okay, here one more name you should remember here. So I told you this is benzyl. See, in this system, this carbocation is in conjugation with this pi electron. No? So this kind of systems are called as allylic carbocations. What is that? Allylic carbocations. So this is allylic carbocation and this should be benzylic carbocation. Okay. So here the next thing is this is benzylic anion, right? So now I am considering the stability of this with this thing, CH2 minus, and here I am writing nitro group. Okay. And one more thing we will be taking here. So let us say here I have here I am writing here OH group. Now tell me, so what are the factors will decide here? So I told you carbene anion is there. So anion means more electron density on these carbons, benzylic position carbon. So that negative charge should be taken towards the ring. Therefore, this carbon will be having less electron density. It will become more stable because negative charge, which is high, making the repulsive interactions in the inside the carbon. So we need to stabilize this negative charge by dragging towards itself. It means if any minus I group or electron withdrawing group is present, the carbene anion is more stable. So I can write electron withdrawing groups increases the stability of carbene anions. Okay, it means just tell me out of these three, so which is electron withdrawing group. So here in the C, compound C, we have electron withdrawing group. So what kind of withdrawing group it is? Strong minus M group now. So it is strong minus M group as well as strong minus I group also. Therefore, this group will withdraw the electrons towards the benzene ring and it will stabilize the negative charge. Okay, so that's how the negative charge is stabilized. The carbene ion is overall it will be getting stabilized. Okay, so what effect this OH group will show? It will show, see, using these lone pairs it can donate. It means this is minus M effect it is showing. It means releasing the electrons. But here in order to stabilize the carbene anion we need withdrawing group, but this is releasing. It means this system is getting destabilized. Okay, so this will be very least stable when we compare with the other two things. Okay, so this effect, this group will show plus M effect and also minus I effect. So but we know plus M effect is dominating group, a dominating effect. Okay, here there is no plus M, there is no groups attached, plus M groups or minus I groups, anything. So it's just benzylic carbocation. So out of this A, B, C, I can say electron withdrawing group present C is more stable than A and least is B. So this is how you need to decide the stability order of carbon anions. Okay, I hope this is also very clear. Okay, so now if I have something like this, NO2, CHO. So this question should be solved based on that orders which I have mentioned. So which is having more plus M effect, more minus M effect, based on that order we can solve this question. So tell me, out of these carbon anions, which carbon anion is more stable? So I told you the minus M effect, see all of these three things are minus M groups only, but out of the three, the nitro group is having more minus M character than this cyano group, then this aldehyde group. Therefore, this will be stabilized more, because the minus M effect of nitro group is more when we compare with the remaining two things. So what is the overall stability order here? A, B, C. So A will be more stable, then this cyano group C, then B. So this is how you need to tackle the question. Okay, so I hope you got some clarity on this. So I just wanted to give one question as homework here. So question number 1, homework question number 1 you can consider. So here I am writing CH2 negative, okay, and here I am writing CH2 CH negative. Okay, so I just want to give them separately first. So first question is here, A, option B is So this is a previously asked JEE question, A, B and C. One aldehyde group, and I just want to add one more option to this, and D is here I just want to add OH group. So decide the stability order of these carbon anions. So this is the first question, and here you can take second question here. So this carbon anion should be called as vinylic carbon anion. Okay, so this is A, and B should be CH2 CH negative charge is there na? So let us change this hydrogen with one methyl group. So I am attaching a methyl group over here for B, and C option is something like this, some nitro group let us add. So just decide these basic questions, these are basic questions, you just try to answer these questions first, okay. One, I need to take it as homework. So by this I can conclude, I can consider that you are clear with at least some basic concepts of carbon anions and carbocation stability orders using mesomeric effect. Okay, this is nitro group here, NO2 group. Okay, so let us discuss. See, stability of free radicals also similar to that of stability of carbocations, the factors which decide the stability order. For example, here I have CH2 free radical like this, allylic free radical, and I have free radical like this, but at this position I have some aldehyde group. So tell me, out of this AB, which is more stable? So we know this here this carbon is having only 7 electrons. It means electron releasing group stabilizes these free radicals. It means electron should be released like this, but we have here one electron withdrawing group, which means it will only withdraw the electrons towards itself right? So it means this carbon free radical is getting destabilized when we compare with this. Therefore, because here it is completely donated like this, electrons can be donated like this, okay, and we can get a conjugative resonating structure like this. So when it is coming here, see this electron and this one electron of this bond will be paired up here, and one electron will be remaining here like a dot. So this is how the resonating structures are possible here, but not here. Therefore, I can say A is more stable than B. Okay, this is clear, I think. Okay, let us move forward. So what I told you, delocalization of charge increases the stability of intermediates. Okay, so more the number of delocalization resonating structure, more will be the stability of that particular compound. Okay, so we need to discuss the acidic nature of phenols and acidic nature of carboxylic acids and basic nature of amines, and we need to compare basic nature of aliphatic aromatic amines also. Okay, so now, so just give a try for this particular question. So we will be discussing about this thing in the next part. So I will be doing the part 2 of this mesomeric effect. So just follow that class also. So thank you for watching. So please stay tuned with the this channel. So we will be giving more updates regarding the NEET exam and the preparation methods.